Assalamualaikum and hi everyone. My name is Ahmad Ishak bin Abdulaziz and my supervisor is Madam Nurjannah binti Yuri, and I'm delighted to present my final year project to you today. The title of my project is Pyrolysis of Empty Fruit Bunches, EFB Palm in Production of Biochar. This is the table of contents. So let's come with the first part, which is introduction. For the background of the study, Malaysia is a major producer of palm oil, which is utilizing every part of the palm oil tree, including the biomass produced during processing. According to Yan, the biomass from palm oil, particularly the empty fruit bunches or EFB, is considered a renewable energy resource with potential benefits. Pyrolysis is a thermodegradation process of the chemical components of biomass that occurs at temperatures ranging from 400 to 800 degrees Celsius in the absence of oxygen. According to Ferreira, this technique enables the conversion of various lignocellulosic feedstock, yielding three types of product, which is biochar, biooil, and biogas. For the problem statement, first is a high moisture content. AFB as a feedstock for biochar production often contains a high moisture content. This poses difficulties during the pyrolysis process as the excess moisture requires additional energy to evaporate, resulting in decreased pyrolysis efficiency and increased energy requirements. Secondly is a low energy density. EFB exhibits a poor calorific value due to its composition and moisture content. The low energy density of EFB poses challenges in achieving optimal temperature during pyrolysis, impacting the production efficiency and quality of biochar. Thirdly is the ash content and alkaline material. EFB contains a significant amount of ash, and the ash itself often contains alkaline materials. The objective of this project is to investigate the effect of different temperature in 500 degrees C, 600 degrees C, and 700 degrees C on empty fruit bunch analysis. Secondly is to study proximate analysis and ultimate analysis of biochar sample using ASTM method. And thirdly is to determine chemical functional group of biochar used in Fourier transform infrared instrument, which is FTR. And then we go to the second part, which is a literature review. In this literature review, first is a biochar on potential solid fuel. Biochar derived from EFB exhibit promising properties that make it suitable for various applications. It improves soil structure, water retention, and nutrient availability, leading to enhanced plant growth and crop productivity. Additionally, biochar can sequester carbon, contribute to climate change mitigation, and serve as an effective tool for environmental remediation and sustainable agriculture. Secondly, it is sustainable valorization of AFB waste. Biochar production from AFB offers a sustainable solution for the valorization of agriculture waste generated by the palm oil industry. AFB, which is a significant biomass waste stream, can be converted into biochar through pyrolysis, contributing to waste management practice and the circular economy. The next part is a research methodology. In the preparation of sample, first the EFB were obtained from Taitak palm oil mill in Johor, and then EFB were washed to remove unwanted impurities like dirt, oil and other compounds. Next to EFB were chopped using chopper into a small before being dried in an oven at 60 degrees C for 24 hours. And then the EFB were grinded in the grinder until become small fine pieces with length to 1 until 3 cm. In pyrolysis process, firstly 100 grams of sample EFB were weighed and put into the boat sample before it placed to the reactor. After the pyrolysis was being set up, nitrogen gas was supplied to maintain the inert atmosphere in the reactor to prevent unwanted reaction or combustion. The nitrogen gas flow rate was set up to 2 liters per minute, and then the temperature of 500 degrees C was set up in the rotation time for 1 hour. The condenser also will turn on to produce the liquid or biocrude. After 1 hour, the sample will cool for 24 hours before the biochar sample were collected. The same method was repeated at 600 and 700 degrees C temperatures. For the characterization of sample, proximate analysis were used to characterize the physical properties of the biochar sample. The proximate analysis will test according to STM method. First is a moisture content, which is ASTM D3173. According to this step, approximately of 1 gram of sample is weighed for 3 samples in the crucible. Second, the sample were heated in oven at 105 degrees C for 1 hour. Third, after sample were cooled, the sample will wait for mass loss for the calculation step. Next, we have ash content, which is ASTM D3174. Approximately of 1 gram of sample is weighed for 3 samples in the crucible. Second, the sample were heated in furnace at 750 degrees C for 1 hour. After sample were cooled, the sample will wait for mass loss for the calculation step. And third, we have volatimeter, which is ASTM T3175. Approximately of 1 gram of sample is weighed for 3 samples in the crucible. And second, the sample were heated in furnace at 925 degrees C for 1 hour. And after sample were cooled, the sample will wait for mass loss for the calculation step. Lastly is a fixed carbon, which is ASTM D3172. According to this ASTM, the fixed carbon will determine using the percentage of moisture content, ash content, and volatimeter. In the ultimate analysis, it is used to find the percentage of carbon, nitrogen, sulfur, oxygen, and hydrogen composition. First, approximate of 2.5 mg plus minus of every biochar sample will weighed before it is read and put into the sample plate. Next, the biochar sample will run through the CHNS instrument. Lastly, for FTIR characterization, it used to analyze fractional group composition of AFB and biochar sample. And this sample was scanned at range of wave number 4000 until 650 cm1. So the next part is a result and discussion. As shown in figure 1, as the pyrolysis temperature increased from 500 to 600 degrees C, the char yield decreased from 38.72 to 29.52%. The biochar yield keep decreased at 23.51% at the highest temperature at 700 degrees C. The char yield always decreases with increasing final pyrolysis temperature because as the temperature increases, the thermal decomposition of biomass compound accelerates. This rapid decomposition results in the release of volatile gases and compounds such as carbon dioxide, water vapor, and organic vapor. The increased thermal decomposition leads to the loss of mass, ultimately reducing the overall yield of biochar. Meanwhile, from the result, the crude oil yield increased from 30.3 to 34.8% as the pyrolysis temperature increased from 500 to 600 degrees C. The highest bio-oil yield of 35.1% was obtained at the final pyrolysis temperature of 700 degrees C. Increasing the pyrolysis temperature increased the crude oil yield. It was known that the heavy molecular weight compounds of pyrolysis vapor become active at high temperature. At high temperature, secondary tar destruction may cause a decrease in the oil yield or increase in the gas yield. Lastly, the gas product yields consistently increased with increasing pyrolysis temperature. When the pyrolysis temperature was increased from 500 to 600 degrees C, the gas yield increased from 30.98% to 35.68%. At the pyrolysis temperature of 700 degrees C, the gas yield were 41.39% at the highest. The increase in gas product is thought to occur predominantly due to secondary caking of the pyrolysis vapor at high temperature. Based on the table 2 result, the proximate analysis of the AFB show a high percentage of ash of biochar sample, which is 74.51%. This is because a lot of moisture content and volatile matter were evaporated and removed from sample during pyrolysis process. Meanwhile, fixed carbon show a low percentage of 2.67% only, indicates lower carbon stability and potential for carbon sequestration. Based on this table 3, the composition of carbon are higher in biochar sample when increasing the temperature indicates greater carbon stability, also carbon sequestration potential and energy value. The presence of nitrogen and sulfur can contribute to the biochar nutrient content, while hydrogen content can affect its energy potential. Meanwhile, lower oxygen content when temperature increase indicates higher carbon stability and reduced susceptibility to further oxidation or degradation. Based on FTR spectral result in Figure 4, for raw EFB, the absorption band in the range of 3300 and 3300 cm1 indicates the presence of hydroxy group at 3282 cm1. Methyl and methylene group, which is alkanes and alkenes, are indicated by the appearance of CH stretch in the range between 3000 and 2800 bands in 2920 and 2858 CM1, and by deformation between 1450 and 1350, which is two bands, which is 1426 and 1368 cm1. The deformation C double bond O with exertion at 1726 cm1 is indicative of the presence of ketone carboxylic acid or aldehyde group between 1280 and 1200 cm1. Bands between 1300 and 1000 cm1, which is band 1022 cm1 and 1232 cm1, correspond to the presence of alcohol, esters, and ethers, showing the CO straight vibration. For biochar 500 degrees C, we can see the C double bond C stretching at exertion band 1536 cm1, and also the deformation stretch CH stretch at 1394 cm1, and C O at 1010 cm1. Same to 600 degrees C, 600 degrees C biochar, we can see there is a 1620 cm1 at C double bond O stretching, and then we have 1380 cm1, which is indicate the deformation stretch CH stretch, and lastly 1002 cm1, which is indicate the CO. And lastly we have biochar 700 degrees C, we have C double bond C bond at 1548 cm1. At this point, we can see there is no peak so much at the 700 degrees C. This is because at higher pyrolysis temperature, the biochar undergoes more extensive carbonization, resulting in a further reduction in the concentration of oxygen-containing functional group. Lastly, we have go through to the conclusion. As for the conclusion, the pyrolysis of empty fruit bunch in the production of biochar provide valuable insight into the effect of different temperature, which is 500, 600, and 700 degrees C on presumed analysis, ultimate analysis, and chemical functional group using FKR. Understanding this effect allows optimization of the pyrolysis process and fine-tuning of biochar properties for desired application. Study emphasize temperature control and characterization technique for EFB-derived biochar, sustainable waste management, and palm oil value-added product generation. For the recommendation, first is optimization of pyrolysis condition for enhanced biochar production from empty fruit bunch of palm oil. This recommendation suggests focusing on optimizing the pyrolysis conditions such as temperature, residence time, and heating rate to achieve higher biochar production yield and improve the quality of biochar derived from EFB. Second is investigating the effects of pyrolysis parameters on biochar yield and quality from palm oil empty fruit bunches. This recommendation emphasizes investigating the influence of quality properties such as carbon content, surface area, and pore structure. And lastly is enhancing biochar properties through optimized pyrolysis of palm oil empty fruit bunch. This recommendation suggests improving the properties of biochar derived from EFB by optimizing the pyrolysis process.